presenting Lab 4 on capacitors. So going into my introduction, the purpose of this lab was to study the effects of time-dependent voltage in both a series and RC circuit. And in order to do this, we were applying the principles that we learned in class to a simulated Java circuit. And this thing includes voltmeters, ammeters, etc. And the plan is to study the outcome. On the next slide, I'll get more into the principles that we're using specifically, but overall what we're going to do is use the loop rule and the node rule to predict the ammeter and voltmeter readings of the simulated circuit. And my end result was that the time constant was 6.11 seconds, but we'll get into how I found that as I continue on. So here we go with the principles. We have energy conservation, current conservation, Ohm's law, I equals V over R, and capacitor laws. So those are basically just about charging and discharging. And we know that charging occurs when the current is flowing through a series with a battery, resistor, and capacitor. And the capacitor will take on more charge until it reaches an equivalent voltage with the battery, and the current will become zero. But on the other hand, discharging occurs when the equivalent voltage of the battery experiences a connection switch between the resistor and the capacitor, and this allows for current to start flowing again, which lets the charge escape the capacitor. And then this discharging is eventually going to stop when the charge equals zero. So we're going to use those laws to study the concept and behaviors of capacitors. Getting into the experiment, we set up a series circuit. I predicted that the series would read 0.02 amps, and in reality I was right. So to do that, I just used Ohm's law. And then next, if we were to reverse the connection of the ammeter, the sign of the original reading also reversed. And then if we were to switch the ammeter and the voltmeter, we would read that the ammeter would be the same, the voltmeter would be 0 volts, and this is all because the current is still flowing in steady state. So moving on to the next few questions in the lab, calculating all the potential differences from each point to point is listed at part 6 there. If you add all of them up, you find that the potential difference is equal to 0, which is what we want it to be. When I graphed it out, you can find that as the electric field increases, the slope will also increase. So that's there in my chart. And again, like we said last time, the ammeter does not change because the current is still flowing. And then next I used Ohm's laws to find the resistance of the resistors and the wire in the ammeter. So those are listed there. Next we did similar experiment with an RC circuit. We found that for the 10 ohm bulb, it lights up and then dims. For the capacitor connected to it, we find it lights up and then dims, similar to what happened before. And this is just showing the charging and discharging of the capacitor. More specifically, for the charge time of the 10 ohm bulb, we found that it charged in 5.89 seconds and discharged in roughly 12 seconds, versus the 20 ohm bulb took longer to charge and discharge at roughly 13 seconds charge and 23 seconds discharge. So because of that, we find that when you increase resistance, it also increases the time it takes for something to fully charge. So going more into my calculations for the RC circuit, we're using the potential difference equations and the equation for change in voltage, manipulating a few things around so that eventually in the end, and feel free to pause and look kind of through this work a little bit more, but in the end we have the natural log of the change in voltage over delta V naught is equal to the natural log of e to the negative t divided by RC, which can be simplified down to negative t over RC. So through these calculations, I was able to predict that the time constant would be 6 seconds, and what I observed is that it's 6.11 seconds, so really wasn't too far off. And there on the right are all of my numbers that I was able to plot for the time versus the change in voltage. So moving on to the final conclusion questions. For the first question, I said that a real ammeter is different than the ideal simulated ammeter because in reality, an ammeter would provide some resistance. Everything provides like some resistance, right? So you can't have something that doesn't provide any resistance at all. So because of this, the current would be slower than in the simulation. And that kind of leads into the second question, similar answer. Without a resistor, the capacitor would charge instantly, but in reality, there's always going to be some resistance. So the model prediction could not happen in real life because an instant charge is not something that could actually happen. So that concludes my presentation. Thank you so much for listening, and yeah.